So, thanks for coming to this talk. My name is Ben Walker. I'm a developer relations engineer here at Meta, which means I talk to other programmers about how to program for the Meta Quest for a living. Before we start, I want to say, please silence your phones. You're going to get an email from GDC asking you to take a survey. Please fill it out. There's also a survey from Meta. Please fill out both of the surveys. Wow. Anyhow, this talk is slightly different from the other talks that you're going to see on like this meta track we have at GDC, because I am not talking about anything new over the past year. So I'm mostly actually discussing two older tools called Compositor Layers and Application SpaceWarp. These have both been around for at least 2 years. This is actually an opinionated talk. I have shipped games at studios ranging from 5 people large to 300 people, and I think all of the tools are useful for teams developing VR, XR, AR type apps, anything in the MetaQuest ecosystem for teams from 5 to 300. So hopefully you all will like learn a lot of stuff to take away. I hope to be your guide through a land of thousands of pages of documentation and to show you how to make the most of the magic of MetaQuest. That's the name. To that end, you can download a copy of this presentation at the QR code on screen. That seems like it'll increase the likelihood of this talk sticking in everyone's brains. You know, there's going to be a lot of websites that I'm going to be linking here. There's going to be a lot of dense stuff, and I want you to have the ability to actually check these websites later and not write down a URL in your notebook. While this is up, by the way, I want to do a quick demographic poll. Could you raise your hand if you're a professional VR developer? You have made money in VR apps. All right, cool. You can put them down. Could you raise your hand if you're like a hobbyist VR developer? You've kind of done some tests. You've switched to dev mode. All right, yeah. And can you raise your hand if you're just like, you're here for the vibe? You heard that Apple Vision Pro is a thing. I don't know. You just want to learn what's going on here. Cool. No, that's a good breakdown, actually. I'm super glad to see that. So this talk is tuned towards folks with like a baseline awareness of developing on Quest, but hopefully everyone will be able to follow along, learn something new, and like follow all of the logic that we're going to go through. Anyhow, I'm going to start easy. The main thing that makes shipping a game on the Meta Quest different from shipping a game on PC or console is it's battery-powered. Wow. The Quest is a battery-powered device. It does virtual and augmented reality. There's no cords. Everything runs on the headset. There's a lightweight battery that powers everything. This is hopefully really obvious. It's like the #1 thing in our marketing. It's the most basic possible information. But it means we make a lot of architecture decisions differently. It has a lot of knock-on effects. So for instance, we care about battery levels, which is something that you don't hear about in a lot of other game dev locations. We want a Quest that's charged to 100% battery to provide a decently long play session. And because most of the battery power does go to running the CPU and GPU, this means we have a system of what we call CPU and GPU levels. Higher levels mean higher clock speeds, and if you don't fully utilize the CPU or the GPU, we will actually temporarily reduce your clock speeds until you increase your utilization in order to save battery life. This idea also drives this idea of a zero-sum framework that you'll see throughout like MetaQuest documentation. The idea is the Quest is actually running at max capacity. Everything is pretty much 100% duty cycle. In order to get more of something, you have to give something else up. So if you want to access our tip-top clock speeds for CPU or GPU, which are normally inaccessible, you have to give up clock speed in the other one. You have to subtract 1 GPU to get 1 CPU. We also subtract CPU and GPU clock speed from you if you use certain expensive features. Most notably, the one that gets hit most is passthrough. So why is passthrough so expensive? Isn't it just a video feed? Like, what's hard about showing a video feed? It's expensive because not only are we showing you the video feed from the cameras, we're actually warping the video feed from our headset's cameras to move them a couple of centimeters away to be where your eyes are inside the headset. We're trying to match your eye positions to what you see. This is partly done to reduce simulator sickness, so your brain doesn't get confused, doesn't think that your eyes have moved outside of your head. But there's a more important reason, actually, and that is we have hand tracking. And we want the pass-through view of your hand to match where your brain thinks your hand should be. And as this GIF shows here, the difference of just a couple of centimeters between your eye and the headset cameras causes you can see this hand right here. Black is where your hand appears in your eyes, and red is where your hand appears in the camera. It causes really dramatic differences in certain scenarios. And if you don't fix this, then your brain's proprioception, which is your unconscious sense of where your hand is located, it's what makes you automatically catch a thrown ball, or what makes you easily be able to like tap on an X button in a small window with hand tracking. If we don't fix this, then proprioception is completely broken. So if you want pass-through, you have to pay for this. And even if you're using pass-through with a controller-based application, you still do want this because we also use this exact same system to align your held controllers with the representation of your controllers in-game. So it is required for pass-through, and it reduces your CPU and GPU levels. I also want to mention, because this is a common question that I get for people who are doing applications that use pass-through. Your application has no idea what the pass-through environment looks like, and you cannot read arbitrary pixels on the pass-through environment. All your app renders and all that the operating system will let you know exists is what you see on the left. We add in pass-through later in order to create the frame on the right that is ultimately presented to the user. This is for security, so that apps can't store photos of your living room. This is for latency, because the frame of your living room may be more recent than the frame rendered from your app. And this is also so that other applications can add to the final frame the user sees. You can see we have a developer HUD OVR metrics tool that's kind of overlaid on top of this right here. So there's a system, obviously, that stacks layers, a layer of your living room, a layer of your game, a layer of another app on top. This system that puts together renders like pass-through, like app submitting frames, it's called the Compositor. One of its main jobs is stacking together all of these layers, which come at different frame rates and at different resolutions for final display to the user. And the other one is actually rendering those images to the physical screens that are in the MetaQuest headset. So for a game environment on the left, this is kind of the image that you'll get from Unity or Unreal or your own 3D renderer. What we literally draw to the screens in headset, like the actual monitors, is on the middle and the right here. The first thing you'll notice, the images are all barrel distorted. That's because we use lenses that have something called pincushion distorted. This is the exact opposite distortion. They cancel each other out. This lets us use simpler lenses, and it also puts more pixels on the center of the screen, so we kind of see it as like a real win-win scenario. Also, just kind of interest of note, the MetaQuest 2 renders both eyes to one screen. So you can see in these two images, the top has the distance between eyes set to minimum. The bottom has distance between eyes set to maximum. And that actually affects the render, what we show on our monitors. The MetaQuest 3, meanwhile, has one screen per eye. So the screens move with the lenses. But those screens are installed 21 degrees rotated. So you can see there's rotation on those screens. The rotation is undone by the fact that the monitors are literally installed rotated, because that kind of gives the monitors your eyes are more likely to land on the monitors as you look around. So this is interesting information, but you mostly don't need to think about this. This is a problem that's meant to be solved by the hardware manufacturer and the operating system, and every individual game isn't supposed to think about, whether you have 2 monitors or 1 monitor in your Quest headset. But this actually is important to know because, well, first I need to do a tangent into resampling textures. So what I have here is a 300 by 300 texture. It has lorem ipsum text. It's rendered in Photoshop. It's like fine. It's a very reasonable implementation of text in an image. At the bottom, we have a 4x zoom, so you can see individual pixels. And here's that texture scaled down to 80%. This is using bilinear filtering, the really average filtering mechanism. What's surprising is you might notice that despite scaling it down, the text seems to get less crisp, which is weird, but we'll cover why. Here's that scaled down texture with a very small amount of barrel distortion again. You can see that the text, it's gotten really blurry. Reading it is actually no longer a good experience. That's all across the text. It's not a matter of the barrel distortion itself increasing or reducing the size of a pixel. The problem you're seeing is that every time you transform a texture and re-render it and pass that on to the next stage to be transformed and re-rendered again, you're resampling your texture. And roughly speaking, resampling will blur it by half a pixel, and these half-pixel blurs, they stack on top of each other, and they reduce crispness, which is really bad for mostly user interfaces and any time you're reading text. And when you take a source texture of some text and you render that into an in-world menu or a dialog box in your scene, and then you have this compositor taking your render of your scene and kind of distorting it and placing it on a monitor, this is the exact same chain of transforms and re-renders, and it applies the exact same amount of blur. This screen, by the way, is from Ultimate Glove Ball. It's an open source sample we publish. You can get it at github.com/OculusSamples. And it's a very great sample. It's not meant to showcase text rendering, so I'm sorry to pick on the team that made it. But the point is, this is a simple way to render text that you kind of would assume by default. You take the source texture, you render on an in-world mesh in game, and you send it through the compositor. The sharpness of the text suffers when you do this. So how do you solve this? If you want a good text reading experience, which this is not, how do you figure out how to make a good text reading experience on the Quest? There's really only one way. You have to make the transformation from input texture to in-world render and the transformation from in-world render to the lens distorted output. You have to combine them into one transformation. So that's what we do. The system that we allow you to take an input texture and render it directly to the screen with as little blurring as possible, it's called Compositor Layers. The idea is you tell the Quest operating system kind of separately from your game running, or during your game running loop, you tell them, here's a texture, I want you to render it onto a quad or a cylinder or on a skybox, I want you to place it here in the world, and I want you to make it an underlay, have it render under us in this compositor stack of layers. And at the spot that you want it to show up, you render nothing in your game because we will render behind it. You have to render 0 alpha, by the way. And we place it there at compositor time when we're stacking up our layers. And the compositor, it uses a vertex shader that in one pass samples your texture. That's a fragment shader. But in one pass, we sample your texture, we render it in the world, pre-distorted, and it creates a much sharper image, as you can see here. I want to call out, by the way, if you get really into the clean text rabbit hole, like if you're making a reading app for the MetaQuest, the source of that loss of crispness is ultimately plain old bilinear filtering. Reducing the number of instances of bilinear filtering, the number of times you sample your texture, is one really great important way to increase the clarity of your UI. The other way that you can go that is actually more expensive is you can pick different resampling algorithms for filtering your texture. The two shown here are super sampling and sharpening, and although they're quite a bit more expensive, they produce even better text for reading if you're doing reading or virtual desktop or that sort of thing. So if you aren't sure about your app's text quality, just compare your app to built-in apps is maybe the easiest advice that I can give you. On the left, I have our built-in store app. It uses compositor layers. It uses all the right settings. And on the right, I have the Ultimate Glove Ball app that I've been picking on so far. These images of the entire frame on top, they're too scaled down to see it, so check the picture-in-picture and zooms at 400% to really see. But the left image that does everything right, the letters are 10 pixel high. On the right, the letters are 22 pixels high. And if you look at like the bottom bar of the G or the dot of the I, you can see that the 10 pixel high text is actually rendered crisper and is easier to read than the 22 pixel high text. So what I want you to take away from this is if you're making a user interface, if you care about text, you can have about half the text size, and it is a better, easier reading experience if you use compositor layers. They're also great for HD video. Anytime you have something that's kind of projected flat and you want to appear crisp, compositor layers are the answer. Please use them in your app. OK, so I've given this talk to developers one-on-one before. That's my job as a developer relations engineer. And they tell me, thanks for the info about how to render my UI. But my biggest problem is that the Quest is so slow that my app misses its target frame rate. I get where they're coming from. The problem isn't quite as simple as the Quest is slow, although I get why you say that if you come from the console world. Just looking at clock speeds and core counts, though, the Quest 3, it's like on paper somewhere around PlayStation 3 level, which really isn't that bad. It's that, as you may remember from slide 1, the Quest is battery-powered. And lightweight battery-powered 3D rendering devices for some reasons that are more complicated than I think get into this talk, they have to have a different architecture based on the fact that they don't have as much power consumption. This architecture is called tiled rendering. Some other talks in the meta track have mentioned it, and I encourage you to Google it to learn what tiled rendering is. The important takeaway from tiled rendering is some stuff just has different costs than it does on consoles. These are probably the 3 most interesting ones to call out. So the Quest 3 might have CPU and GPU specs similar to PlayStation 3, but you can't just port a PlayStation 3 game over and assume that you'll get similar rendering behaviors. It's not apples to apples. By far the most common issue is number 1, additional render passes cost more. In Unity and Unreal, many systems that are kind of exposed as like press the pretty button, so I'm talking about blurring, bloom, HDR, real-time shadows, deferred rendering, all of these systems are actually implemented as additional render passes. So render passes, additional ones are supported on Quest, but you're paying an additional cost for them that is much higher than Unity and Unreal kind of present to you, because they present things in more of a console and computer-focused world. So you should take a lot more thought and care into picking your render passes, picking what you use the pretty button on for mobile VR than you would use in a normal, like something connected to a wall socket world. So, OK, in my one-on-one talks with developers, I tell them all of that, and they say, thanks for the info about how to optimally use a mobile chipset. But I literally do not care. No one on my team does rendering optimization. How do I reach my target frame rate? Yeah. I'm glad finally people left at that. OK. That one is probably the most common thing that I hear. Other very valid replies include, well, you know, I'm doing a CPU simulation heavy app. The GPU stuff is good, but I'm really interested in talking about how to get more CPU time. Or people can also say, I'm an optimization expert. I have hand-placed my GPU resolves perfectly. I'm at 95% CPU and GPU utilization, and I still want more. So There's a neat system that we offer. We released it about 2.5 years ago, I believe. It's called Application SpaceWarp. Some of our rendering-heavy games, like Assassin's Creed Nexus and Vampire the Masquerade Justice, have already released with it. The system is called Application SpaceWarp. So the idea is your game renders a frame every couple of milliseconds. Here's 3 frames in a row. Time increases as you go down. But what if the Quest synthesized every other frame for you? If it did that, you could have twice as long to generate your frame. Your CPU and GPU would have double the cycles, and you would be able to compute and render a lot more, or a lot better. I mean, this is something we offer. So this is pretty, it looks on paper like it could be a nice thing, but it's fair to be skeptical about this. You might say, hey, inserting generated frames in between provided ones in order to increase frame rate? Isn't that like motion smoothing, the algorithm that when you Google it, the top result tells you how to turn it off? The answer is yes, but also no. So for television motion smoothing, the only data available to the motion smoothing algorithm is a series of RGB frames. In order to use App SpaceWarp, we require that you not only give us your RGB frame and your depth frame, but you have to render extra data for your frame, which is this per pixel motion vector that you can see in the bottom right. Let's take a look at it. So this per pixel motion vector that we require, it's a texture of 16-bit floats. If you split into channels, the red channel shows motion in X, the green channel shows motion in Y, and blue shows motion in Z. This is all calculated per pixel. So you can see at the bottom of the frame, this is a frame of me walking forwards, by the way, where the road moves under my feet as I walk forward. That's where parallax is highest. That's where there's the most screen space motion going on. And so you can see the colors get really dramatic there, where the top of the frame is the sky, and there's no motion there because the sky doesn't move when you move. The guy with the gun is moving differently than the car, that sort of thing. I want to call out, there is very subtle Z motion happening here, by the way. You normally don't see Z motion as much in these motion vector frames because motion on the Z axis in screen space close to you doesn't parallax really hard, the same as motion on the X and Y axis when in screen space really close to you. Parallax is really hard. So that's why you don't see that much in the blue channel. But the point is, what you're seeing is where each pixel is going to move. So with the motion vector information, the moment you submit a frame, we have nearly all the information that we need to generate the following in-between frame. The only thing we wait for, actually, is your head movement, because when we generate these in-between frames, we include additional head movement after your submitted frame when generating the in-between frame. So really good things about this algorithm that are unavailable to TV motion smoothing. Number one, this algorithm doesn't add any latency. Television motion smoothing needs to add latency because it can't generate the in-between until it knows what the next frame looks like. That's not the case for us. Plus, we generate just a higher quality in-between because we have information in the motion vector and depth buffers, which isn't available to other people. So it's actually a pretty fantastic algorithm, and it works. And you can see it right now in Assassin's Creed and a bunch of other games. So some developers see all of this, and they say, oh my gosh, it's a magic bullet. Of course I want twice the CPU and GPU cycles for free. And I get where you're coming from, but hold on. The upsides are very easy to understand, but there's a lot of downsides to cover to App SpaceWarp. Number one, although you're already generating this RGB frame and depth buffer that you're submitting to the OS, if you want to use App SpaceWarp, you have to generate this new motion vector texture. This means modifying every material your game uses to support rendering a new motion vector pass. Any materials that don't render motion vectors will appear to stutter because they will be read as not moving at all in the in-between frames. So if you're using App SpaceWarp kind of as a Hail Mary to reach performance on a game that already is near done, it has a lot of different materials, it has a lot of assets to it, that's a long time you're going to spend patching in motion vector support. And it's not nearly as fun as when you know that you're doing App SpaceWarp from the beginning of a game. Second, even more importantly, App SpaceWarp doesn't play well with transparency. The in-between frames generated by App SpaceWarp only support each individual pixel moving in one direction. Transparency breaks this assumption. The menu in front, we expect it to stay still. The blocks in back, we expect to move. When you use App SpaceWarp, anytime that you are showing a transparent object, you have to ask, is the user focused on the transparent object, or is the user focused on the opaque objects behind it? And then you have whatever the user is focused on, render motion vectors. This is kind of difficult, and this is potentially something that'll, change moment by moment, camera by camera. So really what I'd recommend is if you think you're going to use App SpaceWarp in your game, try removing transparency from your render pipeline as much as possible, because it's always going to be a cursed problem. Third, Fast motion causes artifacts. This is just a fact of life. When we generate an in-between frame, we have to fill in large patches of pixels left behind by a fast-moving object. And we can only guess so well with the information available to us. So if you're holding like a sword waving around right in front of you, where the tip of sword moves really fast and is passing through a bunch of pixels in screen space, that is a type of gameplay that exposes artifacts with SpaceWarp. So that's something to know and judge for yourself if it's too much. Fourth, it's a new render pass. As I was saying, new render passes are expensive on the Meta Quest. That consumes some of your frame time. As a rule of thumb, we say expect 30% of your new frame time to be consumed by generating the motion vectors themselves. So you'd only get 70% more frame time on GPU if you enable SpaceWarp. And I want to say that's a rule of thumb. If you're really vertex heavy, it is possible for you to blow like 100% of your new frame time rendering the motion vectors, and therefore the entire optimization is a wash. So there's something else that you'd want to check before you commit to it. Fifth, when you render half the frames, you increase the latency between a user pressing a button and seeing the corresponding action. You double that latency. We can handle head motion in in-between frames, but we can't handle, for instance, firing the gun when you pull the trigger on in-between frames. So if you're doing kind of an action reflex game where you feel like doubling the amount of input latency would hurt your game, it's another reason to kind of look askance at SpaceWarp. So that's every reason not to use it. I want to call it one last thing, by the way, which is if you start using compositor layers in SpaceWarp and you are getting like very rendering focused, we have a lot of really interesting information that allows you to determine how good it is and how much time you're spending, and it's through a tool called Logcat. Logcat is a tool that ships with Android. It's great, and we have all of our optimization-focused data somewhat hidden inside of it, and you can read about it at the developer link linked there. Whew, okay, so those are two features on the Quest that I think add a lot of magic. They're pretty dense. They require a deep understanding of the physical realities of VR, but we're over that hump. Now I want to get to some of the easier to understand features. I just want to make sure you guys know about them because, frankly, they're really cool. They don't require as much backstory, so this will move a bit faster. Number one, we just released last year, actually, Meta XR Simulator. The idea is many games can only be tested by running natively in headset if you use mixed reality or hand tracking. Then previously Play and Editor didn't really let you do things that were important to your core loop. This sucks. It means that you have to create an Android build, deploy it to headset, put the headset on, get to the point where you're testing a change. It slows down iteration time way too much. So we have this app that just last year came out called Meta XR Simulator. You can get it today. It integrates into Unity and Unreal with a package. You can manually integrate it with a native engine. And it sits on top of Play and Editor functionality. So you hit Play and Editor in Unreal or Unity, and you still have all of the access to your windows, and it displays a new window that has a whole bunch of really nice Meta XR specific controls, such as fake pass-through, fake hand tracking. You can record hand tracking and play it back later. It's a great tool for reducing iteration time when you want to, make sure that something pass-through works without deploying to your headset. This one's kind of a personal frustration of mine because it's useful information. It's publicly available, and no one seems to know it. The controllers released with every generation of Quest have different haptics abilities. The Quest 2's haptics motor only works in narrow frequency band. Quest 3's haptics motor can hit more frequencies and amplitudes. The Quest Pro has the same main haptics motor as the Quest 3, but it also adds trigger haptics motors for localized interaction feedback. This is all really cool stuff. Please know that it exists, and know that also we have something called Haptic Studio. Haptic Studio makes it that you don't have to know it all exists. Haptic Studio, the idea is you can load a WAV file, and it will generate whatever are the correct haptics for both Quest 2, Quest 3, and Quest Pro, and you kind of just save out a .haptics file and load it into your engine, and it looks up what you're playing and plays the correct haptics for you. It's also just really good software. I don't know, I think it's very pretty and cool. If you're interested in high-quality haptics, please check out Haptic Studio at the link on the slide. We also released our own version of RenderDoc. So Unity and Unreal have GPU profilers. They're fine. RenderDoc is the gold standard. It's what you use if you have a native engine. It works perfectly fine with Unity and Unreal apps, and it's platform agnostic, and it's very good GPU debugging software. We release our own fork of RenderDoc also that makes it really easy to connect to your Quest headset to capture a frame, and it adds information specific to the mobile rendering tools that we use, these tile-based rendering. You can see tile timelines. You can see heat maps. And I would just want to call out, a lot of people get scared about phrases like GPU debugging. A lot of people kind of see themselves as generalist programmers, and like, GPU debugging is this black art by wizards. It's really not that hard, actually. Like, please download it. It's free off of our website, and just play with it for 2 hours. You'll find that the most important parts of RenderDoc, which are how many render passes do you have, what do they do, and what are their inputs and outputs, are like very easily answerable by this. So please don't be scared. It's like really great software. I'm a huge fan. RenderDoc Meta Fork is what you use for debugging rendering issues on the GPU. But if your CPU is the bottleneck, you'll want to use Perfetto to see what's taking so long on the CPU. This one's even easier than RenderDoc, honestly. The functionality to record Perfetto CPU traces is built into the MetaQuest Developer Hub. Perfetto itself is well-documented software for Android. It's not even our own software. Anyhow, it's great. Google team does a good job on it. This is maybe our newest tool. I think this is really smart. It's stepping a little bit outside of exclusively programmer into design tools. But as you get close to releasing your game, you'll make a listing for your game on the MetaQuest store. It doesn't have to be public or final quality or anything. And then you can invite users to beta channels for your game through the MetaQuest store. They download like downloading anything else. You can even generate a URL and post it on your Discord, and anyone who clicks the URL can get access to this beta channel of your game. If a user is playing your game that they downloaded through a beta channel, through your like MetaQuest store listing, every time they hit the menu button when they pull up the menu for your game, they'll see this brand new Provide Playtest Feedback to Developer button. If they click it, it takes them to a form. The users can fill out whatever they want. They can attach images or videos, and they'll send it to you, and you get to see it on your dashboard on the back end for your store page. This information, in addition to whatever they fill out, this notably also tells you about the headset that they're on, the operating system they're on, and most importantly, the version of your game that they filled out the feedback on, which is historically really difficult playtesting data to get. So I just want to call out, this is actually like the easiest system I know for deploying builds to playtesters and getting metadata from playtesters about the stuff that they're doing. It's a really good system, and please use it. Please know that it exists. And that's it. Thanks for listening. Once again, you can download the presentation here. I hope you learned a lot. I want to call out also in a couple minutes, I'm going to switch to Meta's QR code for feedback. Please fill out Meta's feedback. It looks like we have 3 minutes left, so if we have questions, we can do it for 3 minutes. And please come up to the microphone right there and speak into the microphone.
Hi, thanks, Ben. Great presentation. Application SpaceWarp, do we have to turn that on, or does the operating system turn it on for us? I didn't catch that part.
Oh, sorry, good question. You do have to turn it on.
Okay.
So you have to you can turn it on and off at different points in your app if you want. Generally, people turn it on immediately at the start of their app and leave it on the entire time. But yes, you will have to turn it on yourself.
Awesome, thank you.
Hello. Thank you for your presentation. I found it really enlightening. My name is Miles. I'm a student. So a couple questions I had is first for accessibility. So we're seeing a lot of people who would want to use the MetaQuest 2 or the MetaQuest 3 have like augment. What is the solution in hardware for this, or is there like really no one?
That's a good question, yeah. It's difficult. We have glasses spacers. You can get lenses that support certain like accessibility features, like increasing text. There are, I believe, operating system tools for zooming, but the fact is we don't have great answers for all accessibility things. We do have, we call them VRCs, virtual reality checklists, I believe. We have a series of accessibility VRCs that we encourage apps to follow, and they're for things like one-handed use and low vision use, but they are not required. So it's a bit of an app-to-app dependent thing right now.
Cool. And my other question was about the Meta XR and like unity testing or Unreal testing. So does that work on top of like as something outside of the OpenXR that exists today, like the plugin, or like on top of it, or?
I'm not positive, but I believe you would need to use OpenXR as the bottom of your stack in order to use it. But I could be wrong as I check the documentation to answer.
Cool. Thank you so much.
Hi, SpaceWarp looks really good, and is it compatible with Quest 2?
It is, absolutely it is.
Okay, thank you.
All right, I think that's it. Thanks. Can you switch